So I'm going to be talking to you about the landform regions of Iowa. And this is really important because the way that the land is made due to geologic process really sets up everything that can go on, plant-wise, soil-wise, water-wise. It all is affected by the geology. And Iowa is a really unique region and has a bunch of interesting areas in it. And I'm going to tell you how they came to be and what they are. So this is what we're going to be looking at. We're going to be looking at Iowa. And you've commonly heard of it called the land between two rivers, Hawkeye State, some people call that, which is great because I work for the University of Iowa. I really like that. The thing that we're going to be talking about, though, is how this state kind of came to be. And in that, we're going to be talking about different regions. And these are the landform regions of Iowa. They're designated based on slope, topography, and soils. And so if we break them apart into different categories, we can talk about them as distinct units. And we need to start with this. This is the topography, and this is something I stare at every day because it's phenomenal, it's beautiful, and it tells you so much about what's going on. And you can see that there are what look like smudges that come down into Iowa and stop right at Des Moines. And there's another similar one that stops at the Missouri River. Well, those are glacial tracks. Those are the paths of ice sheets that descended into the state from Canada and Minnesota about 18 to 20,000 years ago. And glaciation is one of the most important things in Iowa. Personally, I think it's the best place on Earth to study quaternary geology, which is the last 2.5 million years, because we have a lot of glacial sediments and a lot of glacial stratigraphy. And this is what I mean by that. There's a lot going on because there's multiple ice advances. So we have the youngest at 18,000 years, that forms the Des Moines Lobe, which stops at Des Moines. And then we have another glaciation to the east and west of that are roughly 30 to 40,000 years old. I got my master's degree showing the ages of those using radiocarbon dating. And then we have the Illinoisan advance that comes in from the east, and that's a really interesting glacial sediment because it's full of coal, because it's scraped up coal from Illinois, and all that sediment has coal chunks in it. And then the rest of the state is covered by multiple glaciations that date back to 2.5 million years, and those have been covered by other ones and modified by subsequent glaciations. So one of the things that I really want to stress is that you can look at the topography of Iowa, and that will tell you a lot about it. It's like reading tea leaves, if you want to say it that way, or a book, because the topography is like a language. You can look at certain ways that streams are shaped, their valley profiles, their slopes, and read what happened. You can read the history of an area based on that. And thus it's a really important part of these landform regions, because slope and topography control what kind of vegetation and farming practices can occur here. So in Iowa, there's three real big players in how this state came to be. The first is Bedrock, clearly because it's colloquially used. It's bedrock of everything. Well, where do you think that phrase came from? The bedrock is the foundation. That's what everything sits upon. And then there's interplay between bedrock and glaciation, ice advance, and then the subsequent rivers that form after that ice retreats. And those rivers are often put in place by glaciers because they're giant blocks of ice that melt. I mean, think about it. Some of these lobes, these ice lobes, came down and were 600 to 1,000 yards tall. These are huge things. And when they melt, they're going to put out a lot of water, and that water is going to set up the rivers. And so there's an interplay of where glaciation can go based on the bedrock, and then the rivers control what happens afterwards, and then they can also cut into glacial sediment and bedrock. So it's not really a rock, paper, scissors. It's more of a different thing. I can't think of the analogy. And then the last piece that is not as dominant on the landscape, but is really important, is loess, wind-blown sediment derived from glacial outwash. And so this loess blew onto the landscape as the glaciers were advancing and retreating. So bedrock, we're going to get into these a little more here. Bedrock was here first, clearly, because everything is on top of the bedrock, which makes sense. It's not like you can take a geologic material and shunt something underneath it. Geology happens in layers, and the law of superposition means that the youngest stuff is generally on top. And so bedrock controls where ice goes. It controls how rivers look. For instance, areas in northeastern Iowa where bedrock is close to the surface have really deeply incised, narrow valleys, and that changes the characteristics of the water itself. Whereas the Iowa River, right here, you can see how wide it is. That's because it doesn't encounter any bedrock from Tama all the way to Coralville. There's areas there at 300 feet of glacial sediment, and that soft sediment allows the Iowa River to meander and cause a really wide valley. I'm currently mapping Benton County, and part of the Iowa River is in there, and it's just so phenomenally wide. It's great. So the contrast that makes Iowa really interesting is that there's areas of shallow bedrock and deep bedrock, so bedrock outcrop and really deep areas of it within miles of each other, and that doesn't occur in a lot of areas around the world because, like in Wisconsin, bedrock is generally close to the surface. It's only Iowa and Minnesota that really show that relationship, in parts of the Dakotas as well. So glaciation is recent in terms of geologic history. And as a geologist, it really tickles me when people say, oh, that process, it occurs at a glacial pace. Well, a glacial pace in terms of geologic time is an instant. Ice comes down in thousands of years, where geologists talk in millions and billions. So these are really quick things. And because of that, they really change how the landscape behaves. Because rivers are diverted by these giant sheets of ice, it deposits material and erodes it, so you can really change how the landscape looks. It makes a new surface and it sets rivers in place. And how it does that is because of the mass of the ice and the fact that it both pushes and erodes materials. So this is a model I've made that kind of illustrates that. So imagine this is the Des Moines Lobe coming down, and this is the old Des Moines River right in here. Let's see if there we go. This is the Des Moines River, and it used to go a little bit more towards the north. But the Des Moines Lobe came down and pushed that river out of the way because it's a giant ice sheet that carries sediment and melts. So it really reroutes all these rivers. But as it comes down, it forms moraines. And these hills are the high spots on the landscape as the ice retreats, because it covers in the valleys, leaving these moraines high and mighty, if you want to say that. But as the highest point of the landscape, the rivers are going to react to that. And so as the ice retreats, it can also go back and forth and create other moraines. And these moraines then act as the high point again. And so you get this really unique relationship between rivers and this front of this ice slope. It's a curved feature because ice comes in and spreads out. And as it retreats, it's going to retreat in a similar fashion because it's thinner on the peripheries and it's going to melt up the axis. And as it does that, you'll get rivers forming into that same curve. That's a really unique thing, and that pattern is only found in glaciated regions. Elsewise, it's usually dendritic drainages, so really angular. The way that tributaries enter the main drainage is not 90 degrees, but very, very acute. And then after the lobe retreats the entire way, you have that drainage network. And since Iowa sits on the stable craton, there's not mountains rising or lowering, so that's what's going to stay. These ice sheets put things in place, and they're not going to be eroded until another ice sheet comes in place. And we can see the overall effect on the rivers. If we just look at North America, you can see the Platte River, which I think is the modern, or should be used as the example of how rivers should behave in areas basically to the Appalachians, because the Rockies are so high, they shut off so much sediment, and that material is going to cover as it goes east. But things drastically change when you reach this red line. That red line is the maximum extent of glaciation. And you can see the orientation of the rivers changes dramatically because of that. So you change from west to east into north to south because the ice flowed north to south. It pushed these rivers in place and set up these drainages. And these rivers then affect what's going on after glacial retreat. And these are the most important things now because, well, in Iowa, there's so many rivers because of successive time after glaciation. So after the ice retreats, you have primary rivers like the Des Moines and the Skunk and Boone, and then smaller drainages form off that. And as time goes on, the number of streams and creeks grows. It's like wrinkles on a face. You know, I might look so young and prim, but I'm 32. In 5 years, I might have more wrinkles than I can count. Well, hopefully not if I wear enough sunscreen. But the thing is, as time goes on, you get more incision, you get more drainages, you drain the landscape more efficiently. So that's why the Des Moines Lobe needs all the tiling, because it hasn't been naturally drained. Other areas in Iowa, like the southern Iowa drift plain down here, have that drainage, so you don't need that tiling. The Iowan surface over here is a different story, but it's more similar to the Des Moines Lobe than to the southern Iowa drift plain. And the other thing about rivers is they act as a loess source. So as ice advances, it melts, puts out sands and gravels, and those sands and gravels act as a source for loess. The wind blows that material onto the landscape, and loess is so great for growing crops in. That's the reason why there is such fertile ground across most of the state that isn't in the very center, because loess can drain water, but it still holds it, and it has nutrients, but isn't too rich in any one. So it's a great medium for growing materials in. And the other thing too is these rivers control how the post-glacial landscape looks based on slope. So the steeper your slope, the more incision you're going to have. And the difference between the Cedar River, which is a river I've mapped my entire career, first starting in Floyd and Mitchell County, then in Benton, and next year I'll be in Muscatine, so I'll map most of it. Comparing the Cedar to the upper Iowa, sorry, this is the Volga, and looking at the slope, you can see that the Cedar has a much lower slope. So what that means is it has less energy to cut down into the landscape. And that's why the Cedar doesn't have a super deep valley like the Volga does, because the Volga and the Cedar both drain in the Mississippi, but the Volga only goes less than 100 kilometers, but the Cedar takes 400 to go relatively the same elevation drop. So that's one of the reasons that the Paleozoic Plateau in this part of northeast Iowa has its unique topography. It's not because it wasn't glaciated. If any of you ever call it the driftless region, I will come and start crying a little bit because you forgot what I've told you. But it has been glaciated. It's because of the direction of the river flow that puts that unique topography in place. So the last thing is wind-blown loess. And loess, again, is caused by wind picking up material laid down by melting glaciers. And there's all kinds of sizes in there, from coarse sands and gravels. You know, some outwash has had gravel the size of my fist, all the way to clay. And what happens is ice melts in the summertime because it's a giant block of ice, and it still got warm in Iowa relatively compared to the winter, but it got above freezing, so that ice would melt. And then in the fall, it would start to freeze again. And then the drainages would shut down and you wouldn't get meltwater. So what would happen is you have these giant braided networks sitting exposed to the wind, and the wind would just pick up material and blow it across the landscape. And that covered most of Iowa with this windblown silt. except there's two areas, the Des Moines Lobe and most of the Iowan surface, that lack that loess. And it's a really interesting question. Why? The Des Moines Lobe is pretty obvious because you're not going to be able to cover material with glacial sediment if it's still covered by an ice sheet. It makes sense because if you have dust falling on an ice sheet, it's just going to melt and drain out through the rivers. To the east of that, the Iowan surface is a different, very, very unique area, and it's a really complicated explanation. So based on these factors, based on the bedrock, the glaciation, the rivers, we can kind of make this this methodology of what's really controlling these landform regions. So this is new. You're the first group that this is being presented to. So I don't know if you should be scared or honored or angry. I'm not sure. I can't see your faces, so I can't see your reaction. But based on these, each landform region has a unique signature based on these underlying factors. The Des Moines Lobe has a high glacial input because it's the remains of the last ice sheet. So it doesn't have any loess, so that's not a factor. And the rivers aren't as important because the area doesn't have incision. The Loess Hills, on the other hand, are just giant piles of loess in western Iowa. So of course they're going to have the highest input, and the controlling factor is that loess. Northeast Iowa, the Paleozoic Plateau, it's all about the bedrock and it's all about the rivers. Whereas the southern Iowa drift plain doesn't have much bedrock outcrop, but it has a lot of rivers forming it. And it also has loess and glacial advances. So bedrock isn't as important as those other factors. The alluvial plains on the Mississippi and Missouri clearly are dominated by rivers. And the Iowan erosions, or the Iowan erosion surface, as it's also known, has everything as a mediumly important factor. So if we look back at the state, and if we look at these regions, this is what's going on. You have glacial control here, bedrock in the area where there's a lot of topography, and in northwest Iowa, ice advance is also important. So let's go into them. Let's break these down and see their unique characteristics. One of them is obviously the topography. So I've been showing you this, and the deeper the blue, the more slope, so the steeper the area. And you can see the Des Moines Lobe is flat. I grew up between LeGrand and Gilman in Marshall County, and that has topography compared to the other side of the county as you pass State Center. And boy, does it get flat there. And that makes sense because it was a new surface relative to where I grew up. Southern Iowa is even older, so it's going to have more slope. So let's start with the Des Moines Lobe. It's in the very center of the state. It's named the Des Moines Lobe because of the fact that it ends at Des Moines. Or did Des Moines start at the end of the ice sheet? Anyway, that seems like a semantics argument. We're not going to get into that. You can debate that amongst yourselves later. But the main characteristics is it's fresh. It's a new surface. It's freshly exfoliated, and it doesn't have loess cover. But it also has moraines. It has these linear hills formed by ice advance and retreat. The other things that it has is what are called kettle lakes or prairie potholes, and those are left over from when the ice sheet was falling apart and collapsing. So the ice actually broke down and fell apart, and so giant chunks of ice were sitting in the landscape, melting, and then those depressions filled in with sediment or water. So most of the Des Moines Lobe was really thin comparatively to areas in Wisconsin and Minnesota. And so that's why those states have way more lakes than Iowa does, because they had much thicker ice sheets. And so when those fell apart, they had huge chunks of ice. Whereas the Des Moines Lobe was thin, so you got these little ones. So the fresh surface also doesn't allow these areas to drain well. So Iowa, actually, before European-style agriculture, this part of Iowa would have been completely covered with marshes. And that's why this area needs to be extensively tiled and channeled, because it's new. So if we look at the drainage density, how incised this area is, you can see a lot of these streams are actually straight, and that's because there was really just sloughs. There wasn't channelization. There's water moving across the open surface slowly. And if you're farming, that's not great for crops because that means you can't get your equipment in to plant the seeds. So you have to drain those. And these are what these prairie potholes look like when they're filled with water. And this is what the terrain looks like here. So you can see it's just, it's not exactly smooth, but these are, I mean, this is wildly smooth compared to most of the rest of the state. So the Northwest Iowa Plains is very similar to the Des Moines Lobe, except that it was glaciated just a little bit earlier. So instead of 18,000 years ago, it was 30,000 and 40,000 years ago. And the area is flat, but it has channels that are forming in it. And it also has a thin cover of loess because it was that loess formed during the last glacial advance at 27 to 28 or to 18,000 years ago. So there's just a little zone of loess on there over glacial till. So it's not the most wild area, but it is still pretty interesting because of that earlier glacial advance. And the Iowa Geological Survey is really interested in that. So next year we're mapping Storm Lake area, which is right on the border here. So we'll finally get into this part of the state and see what's going on. So check back with that later. And you can see the boundary of that glacial advance by looking at the streams, because the rivers record what's going on. They're like the pens or the ink of the retreating ice, and you can see the curve, a linear pattern based on that ice sheet. And here's an even better view of that. So anyway, I could look at, well, I do look at this slope and GIS information all the time. I can't believe I get paid to do it. It's pretty wild. So one of the most striking areas of Iowa is called the Paleozoic Plateau. It's also called the driftless region, which is, again, incorrect because it has been glaciated. There's areas of till on top of the high ridges in this area. So there's glacial erratics, there's drift, there's that blue clay that people say. In Wisconsin, however, across the river, it truly has never been glaciated. So that's an important thing to note, because that is a very interesting dynamic. Why was one area on one side of a major river glaciated, but the other wasn't? I'm not going to spoil it. You'll have to wait a few years to hear the answer for that. But the unique property of this, once again, isn't caused by the lack of glaciation. It's caused by the orientation of the drainage network. And these drainages go right to the east. So they have a massive amount of downcutting power when compared to like the Cedar and Maquoketa and the Wapsipinicon. So these drainages take, again, a long time to get to the Mississippi, to the base. And the other ones in the Paleozoic Plateau drain straight down. And so this area is dominated by steep topography, and it can be held up because it has hard rocks. These dolomitic rocks are pretty stable. If you were to do this in western Iowa, you'd have more shales, and the topography wouldn't be able to maintain those steep valleys. So the unique properties of these carbonate rocks allows this region to have this really fabulous topography. And in there, you get caves. There's fabulous caves, and also unique things like trout streams and the ice caves. So if you want to learn more about that, I would Google that. There's areas where there's Pleistocene fauna still in existence because of the topography here. So the alluvial plains off of the Mississippi and Missouri rivers are pretty straightforward. They're caused by giant rivers depositing material. Most of it is glacial sediment in both settings. And so as you have giant areas of melting ice, you're going to put out so much sediment because that ice has that in it too. And so these areas are really prone to flooding. What was it, 2 years ago, the Missouri Valley flooded significantly, and they're just so flat that it is easy to really inundate a lot of area quickly because you don't have much topography to overcome. And so these are really important for the development of loess as well, because that sediment was also there during the Lake Wisconsin or the last glacial events. And then that allowed those materials to be deposited on the landscape. And so you can see just how different those zones are. These are all channels too. This is channelized just like parts of the Des Moines Lobe because it's super flat. It doesn't drain fast enough, or in this case, it drains too fast because it's made of sand and gravel. So they have to irrigate a lot of these areas as well. So one of the most interesting things that the Mississippi has done, one of the most interesting things about the Mississippi is that it is relatively recent in Iowa. Well, parts of it. And so we think about the Mississippi River as this unmovable force. It's this giant river. It's the old man river. But that's not the case. Before the last glacial advance, the Mississippi River actually went through Peoria. So it came down from its track here, but actually went into Illinois and flowed down what is now the Illinois River Valley. And so the Mississippi River south of Muscatine is actually the Iowa and Cedar Valleys, and the Des Moines River contributed as well. But 20,000 years ago, an ice sheet came in from Lake Michigan and blocked that river. So what it did was it caused a glacial lake to form in front of that ice, because the river can't punch through a giant sheet of ice. It blocks it up, and there's sediment that the ice contributes as well that acts as a buffer. So once that lake grew large enough, it actually burst and flooded down the Rock River Valley into Illinois, or in Illinois, into the Iowa and the Cedar Valley, and established itself as the modern Mississippi now. So after all of this is the modern drainage. And that occurred only 21,000 years ago. And things like this have been happening in the Midwest since glaciation. The Missouri River has experienced situations like this, the Iowa, the Cedar. All of these rivers were affected by ice, and it's fantastic. And that leads us to the southern Iowa drift plain, which is the most extensive landform region in Iowa. I grew up on it. Some of you are from it if you're in Henry County, and Montgomery and Page also. And the defining characteristic of this area is its rolling topography, because it's old, it's been incised. And you might think, well, but Phil, there's all these little lakes, but those lakes are made by damming up rivers. They're not natural. There are very few natural lakes in Iowa, and most of them are associated with the advance of the Des Moines Lobe. So the other thing that's unique about this area is it has a thick paleosol underneath windblown sediment. So before this loess, this dust was blown in, there was a land surface, and then that sediment blew in and covered it, buried it. And so in most areas, you'll have 10 feet to 20 feet of this loess over a paleosol. So if you dig down on the sides, you'll find a reddish clay, really hard material, and then you get into sandy diamicton or glacial drift or whatever you want to call it. And that's a very unique characteristic of this area. And so you can see this is, where is this? This is near Eddyville, in Wapello County. And you can see all these little blue dots. Well, those blue dots are lakes, but they're not natural. And what's going on is that loess acts as a natural, the loess allows water to move through it preferentially, whereas the till is really clay rich, so it acts as an aquiclude. So water hits that and flows out. So what that does, where the loess and till meet, it forms seeps or springs. And once you dam those up, you can get a nice, beautiful little farm pond where you can go catch bass or frogs or whatever you want to do. So the Loess Hills, though, in western Iowa are much different than the southern Iowa drift plain. They're not rolling hills. They're thick, steep-sided deposits made exclusively of wind-blown silt. Some of these areas have over 100 feet of loess deposited during the last glacial advance, which is some of the highest accumulation in the world. it's just phenomenal. And that loess has very unique properties, allowing for vertical road cuts and gully formation. So this area is just so phenomenal, and it has really great prairies and trees. You should get out there if you haven't. I went out last summer and drilled in it actually, and can tell you from my own eyes that there are over 100 feet of loess in some areas. And based on radiocarbon dating and other things, my advisor, Art Bettis, calculated that in order to form these hills, there had to be 1 pound of dust per square yard each year to form these, the Loess Hills. So can you imagine having your house with your windows open when one of these dust storms comes in? It makes the dust bowl look like the dust saucer. No, that's a pretty bad one. Sorry about that joke. So this loess, the story, the glaciers, all of this combines into the most complicated area in Iowa, known as the Iowan surface or the iron erosion surface. And it's an area that's characterized by flat, gently rolling topography, and there's areas of loess in it, but not extensive. They're very thin. And there's also wind line ridges called Paha. We'll talk about those in a second. So this area is very unique because it lacks that paleosol that's in southern Iowa, that old soil, over most of it. It looks like that soil was stripped. And what's going on is it was stripped by permafrost. So freezing temperatures during the last glacial advance removed most of that area, smoothing it out. And the other thing that one of the other things that was caused by that is there's all kinds of glacial erratics or field stones because of the removal of that paleosol. And as you strip down that till, you can't move those big boulders, and those get those form a lag as you remove material. And then modern freeze thaw brings them to the surface each year. So luckily, I grew up on a farm that had a little bit of loess cover, so I didn't have to pull many of these out of the field. And this is it. So you can see this tan color is the loess, but there's none here. So let's get into a little bit of that, since it's my area of study right now, and talk about these Paha. So I'm mapping Benton County, and I've done a lot of work there. Hopefully I can make the walkabout next week. And one of the unique things about Benton County is there's a lot of Paha, both on and off the Cedar River. And as you can see here, they cut across watersheds. So they can't be caused by running water, or else it'd be oriented to each watershed. So it has to be something different. And the thing that cuts across watersheds is wind. So they were formed by Aeolian processes or wind-dominated processes. So these are the Paha in 3 dimensions on Highway 30 as you come from Cedar Rapids to Tama. And they're pretty high. They stand 40 feet above the landscape, and they're made almost entirely of wind-blown silt. And they've been recognized since the 1800s. So here's a phenomenal lithograph from that time. And you can see the Iowa, the Cedar, and the Wapsie. So what's going on in this area is the interaction of the rivers and the bedrock and the loess, and an ice sheet too, in a roundabout way. So the ice sheet set the Iowa and the Cedar rivers up, but then the last glacial advance, so the ice sheet that set these rivers in place was probably 500,000 years old. But then these rivers then were filled by glacial sediment from the Des Moines Lobe as it melted. And that sediment caused there to be sand. And that sand deflated the landscape. It sandblasted it because these winds were super strong. And in areas where sand could travel, it would kick up the loess. It would blow it away. It would sweep it downwind. But in zones where there was something blocking that sand, you would have dust being preserved. You would have that dust stacking up, and that's what's causing these Paha. It's not water flowing and eroding. It's sand blasting everything, and then leaving areas that are protected from sandblasting with thick loess. And so this is over in Lynn County, and you can see the relationship. Here's some bedrock outcrop in this valley, and behind it, downwind of this, is thick loess. These are Paha. And the result of this is these unique hills that you see all over the place. And the other thing too is, as you remove this material, you expose boulders. So if you imagine this, the original glacial till, and you erode it, and then in areas that are covered with loess, well, guess what? You don't have to remove those field stones. So anyway, this is a very brief introduction to Iowa's landscape. It's based on rock and ice and rivers, and then that is a vector for the loess, for the dust. So these are the principal components of this, and it gives Iowa its unique flavor. So speaking of which, let's look at local areas. And so this is Benton County. This is the area I've been mapping. I'm very familiar with it. I might have driven down every road in the county over the last 3 years. So this is one of my favorite areas that I've ever mapped and looked at. This is Vinton, and if you follow the Cedar River east of Vinton, you see these giant tree-covered hills, and these are similar to Paha, but we're called erosion inliers. But I don't think that's correct, because they're not an old surface. They're depositional areas where loess can deposit. And so there's a giant one here where there's over 80 feet of loess. I had to get a special drill rig in to get through all that loess. In between, however, there's an area where there's all kinds of dunes. And so what's going on is there's bedrock right here and bedrock right here, protecting these areas from the sand that's coming out of the Cedar River. But there's a bedrock trough. There was an old river valley that flowed south but was covered by a subsequent ice sheet. And because of that, there's no bedrock protecting this area, so the wind can just blow all of the sand in here, kicking up all that loess. And the dunes there are 30 feet high, as are these north of the Cedar. In Cerro Gordo, I also have been, well, this is where I first started my career mapping. And the unique thing about Cerro Gordo is the interaction between that 18,000-year-old ice advance in the western part, but the eastern part, you can see, doesn't have much drainage, and that's because it was recently glaciated as well. Only it was 30,000 years ago, not 500,000 years ago, like Benton County. And speaking of glacial advances, Henry County is unique as well because it has that Illinoisan advance. And so there's, I think it's called Ridge Road down here, where the road follows topography, but that topography is set up by the edge of the Illinoisan ice advance. So that road follows that old glacial boundary, and it's just so wild. And you can see it all go all the way up into Louisa County there. So I'll turn it over to whoever is next in the queue here.